In this video, we'll look at modeling fluid systems. The objectives of this lecture are introduce the basic elements of fluid circuits and governing differential equations. These basic elements include the continuity equation. We'll look at force balance, look at fluid tanks, flow through orifice, and fluid intertance. Finally, we'll apply these basic elements to certain fluid circuits and derive the governing differential equations. These include a fluid tank with pipe outlet, and aircraft spoiler hydraulics. Now let's look at the continuity equation. A continuity equation is basically the law of conservation of mass. Basically says that mass cannot be created or destroyed. So let's say there's a tank here and I'm putting in fluid at the rate of Wi. That's the inflow rate. Mass inflow rate is given in kgs per second. Let's say W0 is the mass outflow rate. So we can write the continuity equation as if m dot is the rate of change of mass in the tank / reservoir, I can write m dot is inflow rate minus outflow rate. Now let's look at force balance. In force balance, we're looking at the interaction of a fluid system with a mechanical system. Here we have a fluid cylinder with a piston here. And Wi is the inflow rate into the fluid cylinder, and W0 is the outflow rate in the fluid from the fluid cylinder. The high pressure side and low pressure side. Due to the pressure here, there will be a force exerted on this face of the piston. Due to the pressure here, there will be a force exerted on this face of the piston. So this force in the positive x direction, this force here will be negative x direction. We can write the mass, the force balance for the mass, the piston mass. So m is the mass of the piston, mx double dot equal to sum of all force in the x direction. Now that F sum of all force in the x direction can be written as force on the higher side, high pressure side minus force on the low pressure side. And we know that force is given by pressure times area, where area is the cross-section area of the piston. Similarly on the low pressure side like that. So sum of all force in the x direction is nothing but A times PH minus PL. Now Wi, the mass flow inflow rate, is equal to the mass outflow rate because the fluid is incompressible, so there's no accumulation of mass in the cylinder. So whatever comes in must go out. Now we look at flow through orifice. The orifice is essentially a resistance to mass flow. So you have a tube where you have the high pressure side, low pressure side. This is the orifice. M dot is the mass flow rate to the orifice. I can write the mass flow rate equation as m dot equal to 1 divided by r times ph minus pl to the power of 1 divided by alpha. Or you can write m dot equal to 1 divided by r times delta p to the power of 1 by alpha. Delta p is the difference in pressure, ph minus pl. R is the resistance and alpha is a parameter that denotes either laminar flow when alpha equal to 1 or turbulent flow when alpha equal to 2. You can write the same mass flow rate equation in terms of the volume flow rate. You can write mass flow rate as nothing but density of the fluid times volume flow rate. And volume flow rate is given in meter cubes per second. So you can write Q, which is the volume flow rate, is equal to 1 divided by R times rho times delta P to the power of 1 by alpha. Now fluid inertance is due to fluid flow in a long pipe. What do you mean a long pipe? A long pipe is one where the length of the pipe is much larger than the cross section of the pipe. So it's a thin, long pipe. So fluid is flowing from the high pressure side to the low pressure side. You can consider this entire column as a fluid mass that is accelerating under pressure, under forces due to the pressure from the highest pressure side and low pressure side. So I can write the force balance equation for the fluid column as mx double dot equal to sum of all forces in the x direction, and sum of all forces in the x direction is equal to the force due to the high pressure side, which is A times pH, minus force due to the low pressure, which is A times PL. So this force here will be pointing in the negative x direction, this force here will be pointing in the positive x direction. And I've written the mass of the fluid column as density times area of the pipe times length of the pipe. A times L is the volume, volume times the density is mass. So you can cancel out A, both sides, you get rho L x double dot equal to delta P. Delta P is the pressure differential. You can write the same equation in terms of volume flow rate. You can write the volume flow rate as the area of the pipe, cross-section area of the pipe times velocity of the fluid. Now we assume that the velocity is uniform across the entire area of the pipe. If you've learned from fluid mechanics, that's not typically the case, but this is a simplification that we do when modeling these fluid systems in our class. So V can be written as x dot, and therefore you can write q dot is ax double dot, and you can substitute for x double dot in terms of q dot in this equation to give you rho L divided by A times q dot is equal to delta P. And you can write rho L divided by A as I, and I is the inertance, fluid inertance. Next we'll look at a few examples using these